Okay, so this is number 25 on the final exam review. What is the pH of a 0.5 molar solution of sodium hydroxide? So sodium hydroxide, of course, is one of those things that's known as a strong base because it's a hydroxide of one that makes a B on the periodic table. And so then that's going to break up or dissociate into Na plus and OH minus. And so then this is a 0.005 molar solution. All of this is going to go away, and it's going to become 0.005 in Na plus and 0.005 molar in OH minus. The thing that's interesting to us for the pH is the OH minus. And if you look at the pH square, once you get the OH minus, then you can take the negative log and you can get the POH. So let's do that on our calculator quick. Let's take the negative logarithm of 0.005, hit enter, and we have 2.3 as the POH, and then do 14 minus that answer. Whoops, 14 minus, back that up, 14 minus answer, and that gives me 11.7 then as my pH. And of course it's above 7, so you know that it's basic, which makes sense because this is a base and it's a basic solution. Number 26, the molar concentration of hydronium ions in pure water is 1 times 10 to the negative 7th. You know that from the Kw equation. You know that H plus times OH minus is equal to Kw, which is equal to 1 times 10 to the negative 14th. And so if they're equal to one another in a neutral water solution, you can call this x and this x. And so x squared is equal to 1 times 10 to the negative 14th. Square up both sides of that, and you end up with the H plus or the OH minus ion concentration equal to 1 times 10 to the negative 7th molar. So that's in any water, pure water solution, or a solution that has a pH of 7. Number 27, what is the ratio of base to acid in blood that has a pH of 7.15. For H2CO3, the pKa is 6.73, assume 25 degrees Celsius. So in your equation sheet for acids and bases, it will have the Henderson-Hasselbalch equation right here for buffer solutions. And this, you can tell this is a buffer solution because it's got a weak acid in its conjugate base right here. And so it says the pH is 7.15 pH. And then it tells us the pKa is 6.37 plus the log of the base over the acid. And so what we're looking for then is this ratio of base over acid. So we'll call that X because that's what you usually solve for in math class. So now let's try it on the calculator. 7.15 minus, bringing this to the other side, 6.37. So I have 0.78 now. So 0.78 is equal to the log of the ratio that I'm interested in. So to undo the log, we need the 10 to the x key. So we do 10 to the x, second answer. And so we end up with 6.02. So our ratio would be 6.02 to 1. So there'd be 6 times as much base as acid in this solution of HCO3 to H2CO3. Number 28. The acid dissociation constant for acetic acid is, at equilibrium, the molarity of H plus is, this is the molarity of H plus in a blank solution is. So it wants to know the H plus ion concentration. So let me zoom out just a little bit. Whoops, zoom out so I've got a little bit more room to write. And so we've got acetic acid, and I'm not going to write the entire equation for acetic acid because it's kind of big. And I'm going to write it reacting with water, because when in doubt, react with water. And then when it dissociates, I'm going to get some H3O plus, which is H plus, because I know that H3O and A plus are the same thing. And then I'm going to get some A minus right here. Okay? And it tells me that the molarity of H plus in a 0.382 molar solution. So I have a 0.382 molar solution initially. And water, of course, is a pure liquid, so I don't fill any of that in, and I have to make the assumption that there's none of this and none of this to start with initially. Then, when the acid dissociates, I'm going to lose a certain amount of this, and I'm going to gain that amount over here and that same amount over here because it's a 1-to-1-to-1 ratio. And so this will end up being 0.382 minus x, and this will end up being x, and this will end up being x. And then I can write the equilibrium constant expression and set it equal to the K, and the K is 1.76 times 10 to the negative, I believe that says fifth, and that will equal products, which would be x squared, divided by reactants, which are 0.382, and I'm going to ignore this x and say that it's small in comparison to the 0.382. And now we'll solve for x, and once I find x, well, x is the H3O plus ion concentration. So let's do a little bit of this on the calculator. 1.76, enter exponent, negative fifth, multiply that by 0.382, enter, and then we'll take the square root of that. So second, square root, second, answer, and I have 0.00259. Or if I just want to round that, my H plus ion concentration would be 0.0026 molar. That would be the concentration of H plus at equilibrium. All right, come back in the next video with more.